Welcome to today's Rosseland Lecture. We celebrate the founder of our institute, the Institute of Theoretical Astrophysics. Before he received his PhD in 1927 at the University of Oslo, Svein Rosseland spent time in Copenhagen with Niels Bohr and at Mount Wilson Observatory in California. During his first years as professor of astronomy, the new institute building was built as one of the first buildings here at the Blindern campus. This was in 1934. Its name, the Institute of Theoretical Astrophysics, reflected Svein Rosseland's vision of applying the latest findings in physics to understand the nature of stars, galaxies, and the universe. At the 100th anniversary of Rosseland's birth in 1994, we started a series of annual lectures to honor his memory. We have had many of the world's most famous astrophysicists giving the Rosseland Lecture. This year, we are honored to introduce to you Professor Françoise Combe. Françoise Combe is Emeritus Professor at Collège de France, where she has held the chair of Galaxies and Cosmology since 2014. And she is President of the French Academy of Sciences for 2025 and 2026. Combe works at the Paris Observatory on the formation and evolution of galaxies, their dynamics, and their co-evolution with supermassive black holes, as well as on models of dark matter. She has received several awards, including the CNRS Gold Medal from the French National Center of Scientific Research, the International L'Oréal UNESCO Award for Women in Science, and the Gothenburg Lise Meitner Award. Combe is member of the European Academy and international member of the National Academy of Sciences of the United States. Now we are very excited to hear Professor Françoise Combe on the dark matter puzzle. Please.
Thank you very much, Luc. I'm very honored to have this invitation of Rosseland Lecture. So thank you very much. And so today my presentation will be on the dark matter puzzle. I think that you see my pointer. So my first slide is to just introduce you. You know, we have some halo, dark matter halo around galaxies. It's just a cartoon, just to tell you that dark matter is surrounding galaxies. In fact, it is not dark. In fact, why we call it dark? It's because it is not interacting with photons. It's not emitting, not absorbing the photons, the light. But in fact, it is transparent. Maybe there are plenty of dark matter in this room and you don't see it. So it's not dark, it's transparent. But you have a way to see it. Here you have a galaxy cluster, plenty of galaxies in the front world here. And you have galaxies in the background. And galaxies in the background, their light is deflected by the mass, all the mass which is in between galaxies in the background and the observer. And their light is deformed. You see arcs here. And all this strong lensing and also weak lensing, I will describe that in the presentation, tells you about how much dark matter is there in the universe. So we have a way to cartography, the map of the universe. So just to begin with setting the scene, how much dark matter is there, the content of the universe. Yet you see that normal matter, that are atoms, protons, neutrons, that we call baryons because they are heavy. It's heavy in Greek here. So all the visible matter, the normal matter that we are useful, familiar, and this is only 5% of the total. And the dark matter, which is exotic particles, not atoms, they are 25%, so 5 times more. And the rest is dark energy. I will not speak about dark energy. It's another presentation. But just to tell you that we know now that the content of the universe is like that. But you see that the dark matter, which is exotic particles, is much more massive than the normal matter. And just to give an idea of orders of magnitude, the density of the universe is very, very diluted. You see here, 10 to the minus 29 gram per cubic centimeter, while what you are used here, the water here, is 1 gram per cubic centimeter. So you see, it's huge. The universe is huge, but it's very diluted. So I will begin with a little history. Maybe also a comparison. Here you have, for instance, Urbain Le Verrier, who was the president of Paris Observatory, and he was a very clever calculator of celestial mechanics and the position of the planets in the solar system. And he computed during 6 months. There was no computer, so he was calculating with a paper and a stilo. And after 6 months, he discovered that the last planet that were known at this epoch, Uranus, was very strange in its orbit. Of course, the orbit at the 0th order are very simple. They are Kepler orbits. They are ellipses, but this is not taking into account all the perturbation of the other planets. So we have the torques from Jupiter, torques from Saturn, and so on. So if you compute that, then he discovered that there should be some unseen matter, some invisible matter, or missing mass. And then he computed, well, there must be a planet there. And the day after he published this, it was discovered by John Gall in Berlin, and it was Neptune. So you see, we can discover invisible matter. In 1860, there was another calculation from Le Verrier. He said, well, maybe Mercury is not right also. There is a little discrepancy between the precession. Of course, the precession is normal. It's the torques from the other planets. But there is an excess of precession of 43 arcseconds per century. It's very small. And he said, well, of course, he gained a lot of glory in his discovery here. Why not another one? And then he said, well, between the Sun and Mercury, there could be another planet. Let's call it Vulcan, because it must be very hot, of course. And they waited for this eclipse in 1860 to see it. There was no planet at all. So this mystery kept going until 1916. So you see, you have decades of invisible matter. And then, after that, you have another solution, which is modified gravity. And I make this parallel because I will talk about several solutions for the dark matter, some with exotic particles and some with modified gravity. So modified gravity was Einstein's general relativity, of course, and general relativity predicts this excess of precession of Mercury. So you see, you have 2 ways to solve the problem. So for the first to discover that there could be some missing mass in the universe is Zwicky, that you see here, from Switzerland, but he make all his observations in California. And he has a general idea to observe a coma cluster, a cluster of galaxies where you have thousands of galaxies. And he measured by the Doppler effect the velocities. Velocities are of the order of 1,000 kilometers per second, so very strong velocity. And he tried to balance the kinetic energy, square of the velocity, per unit mass, and also the potential, so all the visible mass. And then there was a big discrepancy, because if it takes only the visible mass, which is stars, essentially, stars in galaxy, then the m/L, the mass-to-light ratio, should be of the order of what you have for the Sun. So if you put it in the Sun units, you should find 1 or even 5. It is a very small star that have more mass for the light. But there you have at least a factor 100. So the mass he needed to make the coma cluster coherent, that is equality between potential energy and kinetic energy, was 100 times the visible mass. So what he said, that was maybe dark matter is in galaxy, or in between galaxies, or even Newton's law is not valid. So again, modified gravity, even at this epoch. But this was not believed at all. In fact, he was a very bad character when you find it here in this photograph. He treated his collaborators of spherical stupid, from all the directions stupid. And he was also he did not believe in the Big Bang. He did not believe in the rotation curve of galaxies. So there was some genial idea, but some others. So it was not believed at all. And then you have to wait for 70s. You have the pioneering work of Vera Rubin that you see here. And she developed a rotation curve with more precision, because just before her there was some rotation curve, of course. So this is the velocity in a vertical direction and the radius from the center of any galaxy. Here it's M31, which is Andromeda, the next spiral galaxy, and M33, the next triangle galaxy, and so on. And you see that there was big error bars. And it was not possible to know if it was flat, not flat, and so on. But she made a very systematic observation of hundreds of rotation curves, and she discovered that finally they were flat. So even when you go far away, where there is no stars, no visible matter, where you will expect that the velocity is going down, like the Keplerian law in the planetary system or the solar system, for instance, you have the velocity that is going down, but here it's not. So you need a lot of matter to explain that the stars and gas are rotating very fast, so that the centrifugal force is compensated by an attractive force. So how you build this rotation curve? You see here you have a galaxy, spiral galaxy, which is rotating in that sense. So the point A is going towards you. So we have a Doppler effect, blue shifted. Here you have the systemic velocity, of course, the expansion of the universe. And then here it is going out, so it's redshifted. And of course, you have two sides of the galaxy, two rotation here. You fold the two to have one curve of rotation. And that's why we can have the rotation velocity. Of course, the two sides are not symmetric in general, but you symmetrize a little bit. So with that, there was also a new way to have the rotation curve and to go farther than the stars is from atomic hydrogen. Atomic hydrogen is the most abundant element in the universe, the first atom. And it was discovered in the 50s that you can have a very interesting radiation at 21 centimeters, radio astronomy, that was discovered. It's hyperfine. And why it is very important? It's because the H1 is very cold. So in general, you have not the electronic transition. You have this hyperfine, and it is normally a forbidden line in the laboratory because it takes 1 million years to spontaneously emit. But since you have a large number of atoms on the line of sight, you see that. And what you see is a rotation curve as a function of distance from the center. And you see that the disk of galaxies are finished here. And with H1, like I put in this diagram, in orange, you have the map that you can do with atomic hydrogen, with this radioastronomical wavelength. And in the center, there is a zoom where you see the optical. What you see with the eye in the visible light is the spiral structure of the galaxy, which is very small, and you can go very far. And the gas is only a few % of the mass, so it's not adding much mass. So you have no mass in this part of the rotation curve. You have no mass. You are outside the visible mass, and you are still very flat in rotation curve. And that's what convinced astronomers that the invisible mass is there. You need a lot of missing mass to explain the rotation curve of galaxies. Now, historically, you begin with optical, you have radio astronomy, and we try to observe all the electromagnetic spectrum, of course. You go to the higher energy now, the X-ray. Of course, X-ray, you have to go to satellites because the X-ray is stopped by the atmosphere. And then in 1966 and other years after, you had a satellite that could observe, for instance, the coma cluster that were observed with Zwicky. And the surprise was that you have a lot of emission, like thermal emission of a gas in the whole cluster. And it's thermal emission, that means it's very high energy. So the temperature that you deduce is 100 million degrees. So it's plasma, of course, you have particles are ionized at this temperature. And it is really a very hot gas. And when you look at the mass needed to radiate this gas, it is 10 times the mass of all the galaxies. So finally, Zwicky has not seen all the mass. Even there was more visible mass than Zwicky has devised by looking at galaxies. In fact, this is 10 times more. So you see the factor 100 that you have, at least you go down to factor 10 because you have factor 10 more. But still, it's not the whole, because you know that, as I show you, that the missing mass is 5 times, at least at the universe scale, 5 times the visible. So you have still to find something else. But at least we discover some of the invisible mass. So you see, it exists, but it is normal baryons. Now, at the scale of the universe, what can we say? We have the galaxy, we have a cluster of galaxies, and now at the global universe, in fact, the general relativity of Einstein tells you that the gravity is not a force like electromagnetic, it's a deformation of space. So mass is just putting some curvature, and the Einstein equations are relating the curvature of the universe to the mass, the density of mass and energy, which is in the universe. So you have 3 possible solutions of these equations. Either you have a very high density. So if it is high density, you are a positive curvature. Well, when I make this very very simple cartoon, the universe is a 2D, because it's difficult to reproduce a curvature of a 3D universe, but the 2D is much better. So imagine that the universe is only the surface of the sphere here, and you see that, of course, the triangle, the 3 angles, the sum of 3 will not be pi, but will be larger. So you can measure this curvature. If omega is larger than a critical density, is there just to have a quantity without dimension and be much simpler. So if it is very dense, you will have a positive curvature and a finite universe. If it is less dense than that, you will have a negative curvature. You see like a saddle here to represent. And if you are exactly at this critical density, you will have a flat universe. And now we know, this is the size of the universe with respect to the time. So we are here, it's now, and we are observing the past here, and we are trying to predict the future. So we are here, and we know now that our universe is in the red curve. Why? Because, well, of course, we are not dense enough that we can go from a big bang to a big crunch here, where the universe will be so dense that it will recollapse. It's not this universe that we are living on. And it is not those either. And we know now, because of the discovery of the dark energy, which is quite recent, in fact, it is 1998, we discovered by some standard candles, that is a supernovae, that the expansion of the universe is not decelerated as it was expected, but it is accelerated. So if it is accelerated, you need a repulsive force. If it is only gravity and attractive force, you will have an expansion and then deceleration of the expansion. Okay? That we astronomers were very surprised to see that the expansion is accelerated. You need some, and this is dark energy, which we don't know at all what is the nature of this dark energy, but at least it provides a repulsive force so that the expansion is accelerated. And we are in this universe here where the size of the universe will be increasing exponentially. Now, how we know that the curvature of the universe is 0, there is no curvature, the universe is flat, is a lot of information has been gained from the cosmic microwave background. What is this? This is the relic radiation of the Big Bang. You know that the universe was starting in the Big Bang where it was very dense and hot, and then it is expanding and going very colder and colder. At some epoch, it begins to be 3,000 Kelvin, and then at this epoch, the particle, charged particle, protons, electrons, recombine to form atoms of hydrogen. So at this epoch, the coupling between the radiation, which is very coupled with charged particles, and the particles is cut, and we call it this recombination, and also the last scattering surface. Why? Because at the beginning, there is a scattering between photons and baryons, and now there is no scattering at all. And what you see at this last scattering surface, you have here the sky seen by the satellite Planck, which was a European satellite launched by the ESA. And here you see that there are fluctuations, very small fluctuations. The colors are false color, of course. When it is hotter, you have orange, colder blue. And you can put all this structure as a function of the angle. You see here you have 90 degrees, 18 degrees, 1 degrees, and small scale picture. And you see that when you plot all the number of pixels which are this perturbation, you see that there is a peak at 1 degree about. The size, 1 degree is particular. And why? It's all these that you see. Well, by the way, all the points of observation are small points, the red points. And you see that error bars are very, very small. So we are very sure, secure of these results. And the model in green passed through all the points, of course. And what are these oscillations? They are oscillations due to acoustic waves, in fact. Acoustic waves, you'll see, well, in the void today, there is no sound, nothing, because there is no air to make pressure. But at this epoch, when there is photons coupled with the baryons, which are ionized, then you have radiation pressure, and you have waves of pressure. You have sound. So the sound in this plasma is known. It's a very well-known perturbation. And you can measure the highest peak of this oscillation, which is the size that has been run by the sound from the Big Bang to this epoch. This epoch is very close to the Big Bang, is 400,000 years, less than 1 million, while the age of the universe is 13 billion years. So you see it's very, very small. And in this period, you can have exactly, you know the linear size of this biggest size. So if you know the linear size and you see the angle, then you see that you can derive the curvature of the universe. And here is the observer, for instance. You have your ruler. You know this size precisely. And you see it with some angle. Here is the red. You see it in the red. If you were seeing with another angle, smaller, then you will have a negative curvature. Okay? The angle will be smaller. But it is not smaller. So finally, you can derive with very high precision that the photons from this surface arrive towards you in straight line. That is, there is no curvature, which is very easy to compute distances in the universe. Because if it is not flat universe, it will be much difficult to compute the distances. So you know how we know a lot of things from the map of the Planck satellite, which give the curvature, but also the amount of dark matter and dark energy in the universe. That's why we know that there is 25%. Now, I showed you the first slide that we can map all the universe, like the geographer from Vermeer here. You map all the universe with dark matter. And it is exactly with this strong lensing that are the arcs here that you see. The arcs come from the galaxies that are in the background, and their light is deflected by the mass that is from the galaxy to the observer. Of course, you have strong lensing here, but all the points here, you have millions of galaxies that are deformed. We call it weak lensing with respect to this strong lensing. And from this is like a little iron that you put in the magnetic field, and then you can see the magnetic lines, in fact. And here is exactly what you can see. Here you have the galaxies in the background. You have some matter here, a cluster, for instance, and the telescope is here. You see that you have a deflection. You can have, if you have, for instance, background galaxies that are all the same shape, just a little circle. Of course, it would be nice to have a simulation of the deflection of the light and finally the final image that you get. Sometimes you have an Einstein ring where you are exactly down the barrel, and sometimes you have a deflection Okay, but of course the galaxies are not all the same shape. You have intrinsic shapes, some are edge-on, some are not. And then you have to rely on statistics, that you have to have thousands or up to 1 million galaxies behind, and then statistically you have a deformation. And that's what is done in big surveys now. And we use, of course, machine learning. When you have millions of galaxies, that's no way that the human eye can only compute the thing. So here is an example of what we do. For instance, you have a simulation to teach the machine, deep learning. Here is a simulation of galaxies, and you try to compute the deflection and the shape of the galaxy behind, and then you make this deep learning here, and the neural networks here that you know very well, because every people in astronomy is using this machine learning, so you know very well this. And finally, you recover what you have put in the beginning. So in the simulation, you know very well. Now, in the true life, you deduce the dark matter image. So here is an example, for instance. We call it the gravitational shear. It's a weak lensing, like a shear. And here you have in red the map of the visible mass. Why? It is the X-ray Chandra image. X-ray image, as I told you, is the hot gas that is most of the baryonic mass in a cluster. So here is the mass of the baryons, a map of the baryons. In blue, you have the total mass that you have deduced from machine learning applied to the gravitational lensing, the weak lensing and strong lensing. And then you can compare. And when you compare it, when you superpose, of course, it's not completely superposable because you have some uncertainties in the map of the dark matter. But at least in the void here you have a void, you have no visible mass, you have no dark matter. So they are really at the same place. You can even make a reconstitution of the dark matter in 3D because you have the redshift and so on. And also, at the scale of the galaxy, we know that there is a very good correlation between the dark matter. So here is the flat portion of the rotation curve of galaxies that were devised by Tully and Fisher. Before the dark matter was known, it was just to have a calibration for to have the distance. But now it's used for dark matter. So you have a proxy for dark matter here, and here you have the baryonic matter. That is visible matter of the stars, and also the gas, when you can measure the gas with a H1 21 centimeter. And you see that there's a very good correlation. We have to explain that, at least either for exotic particle model or for modified gravity. You have to explain this kind of observations. So there's a very good correlation, even if it is not proportional. Because, for instance, in dwarf galaxies, you have more proportionally, we have more dark matter with respect to baryons than in the big galaxies. But this is included in this relation, which is not linear. Now, what is this dark matter? And there are several kinds of dark matter, and it is categorized by the temperature. Temperature means when the structure form, when the matter collapse and dissociate from expansion, then you have either small particles, very small mass. They are relativistic, so they are like photons with a radiation pressure that prevents collapse of the small structure. So when you make a simulation with a hot model, that is particle like neutrinos, very small mass, so they are relativistic, they have radiation pressure, and they prevent the formation of galaxies. They form filaments. When you have cold dark matter, that is massive particles that are not relativistic when they form the structure, then you can have all kinds of structure, which galaxies in filaments. So when you observe the galaxies, it looks like either cold or warm, but never hot. So even if at this epoch we knew that neutrinos, normal neutrinos, have a small mass, finally they cannot be the right answer because they will not form galaxies. Now, what was the best candidate that people had at this epoch in the 80s when we discovered that the particles had to be exotic? In fact, when you look at the standard model, you have as elementary particles. It's not proton and neutrons, it's quarks, because proton and neutrons are made by quarks, which are the yellow particles. You have the leptons, that is electrons, neutrinos, and so on, are in the red things. And then you have the bosons, which are the particles that carry the force. Here, the photons for electromagnetic and others. And we have discovered also this Higgs boson, which was predicted by the standard theory and was discovered in 2012. It is about 100 times the mass of the proton. But then there's no candidate for dark matter. So since in this success of the standard model, a key was the symmetry, in fact, in the particles. So people had idea to suppose that there is supersymmetry. Supersymmetry, all these models had some mirror particles in the other part. And of course, it's not the charged particles that will be interesting, it's only the neutral. So there is a linear combination of all these neutral particles that was the neutralino. Neutralino was the best candidate for the dark matter for 30 years, in fact. And there was a coincidence that make the people talk about a miracle. Miracle, why? Because these very heavy particles, 100 times the mass of the protons about, was interacting only with a weak force, because we don't see it and it's not interacting with the other force. So we know the annihilation cross-section. We know how much it annihilates. It has to be its own antiparticle, because it's neutral and it has no parameter like baryonic number or whatever. So it's antiparticle. So it has to annihilate. So when you look at the number of these particles as a function of time, you begin with a large number, and that it annihilates until when the expansion of the universe is enough. It is so diluted that they have no time to encounter themselves. The collision time is higher than the age of the universe, so they don't collide, they don't annihilate. And then you have a relic abundance. Okay? And you need to have this relic abundance, 25% of the content of the universe. Not only it's not sufficient to find a candidate, it has to be 25% of the content, okay? And then for that, you had to have this mass. And the big problem is that when you reach this mass in 2012, when you discovered the Higgs boson, there was no supersymmetric particle at all. Now we have gone to higher energies, and there is still no supersymmetric particle and no neutralino. So this particle is less probable, while it was the main candidate for a while. And also it was, we have a lot of experiments that try to detect directly this particle, because if there is one in this room, there is also some in the Grand Sasso tunnel here. Why people are putting their detectors in the tunnel? Because you are free from cosmic rays that are stored by the mountain, or neutrinos or whatever. So at least cosmic rays is more, because neutrinos cross the Earth very easily. So at the beginning, there was kilograms of germanium, very purified, so that there is no radioactive events. Now there are tons of xenon, liquid xenon, in the Grand Sasso. And then here in this diagram, you have the cross-section probability to encounter the detector as a function of mass and time here, and there is nothing. Well, there's a bad thing for this particle. Now we are going to this diagram where you have the probability of interacting with the detector and with a function of the mass of the particle. And you see the upper limits are going down, down, down. And you are reaching a plateau here, which is the neutrino. In fact, what you are going to detect now is a neutrino coming from the sun. So as soon as you are reaching this, you will not be able to detect any dark matter particle, because you will detect neutrinos. And this is occurring now. In 2025, that the xenon n-ton, which was 8 tons at this epoch, they published that they are detecting the neutrino of the sun. And very strange, because this is for 30 years. But now the Chinese has made a panda xenon 4 ton. In a few years, they gain from the 30 years experience of the European and American. And they also detected the neutrinos from the sun. Well, by the way, it was another interesting part of this xenon experiment. They detected another unknown radioactive part of the xenon, which has a lifetime much higher than the age of the universe. But since they have 8 tons, they can have a few. And they had 126 events. So they have discovered another radioactive xenon element. But anyway, you see here the first detection of solar neutrinos by the European here and by the Chinese here. Well, they have also some calibration with a source of a neutron source. And I don't enter in the technical details, but the main bottom line is that now they are reaching the detection of neutrinos, which come from the boron 8 in the sun, and now they will not be able to continue this kind of direct detection. Well, now why we need other candidates also? It's because there are many problems with the standard model of cold dark matter, CDM. Here you see a simulations of the cosmic web with a lot of filament. It's only dark matter in these particles, the minimum one. And you see a lot of zoom here. Here you zoom this part here, and you zoom this part here, and so on. And the colors are only the density, because there is only dark matter. But you see that you have, in a galaxy, you have plenty of small dark matter halo around any galaxy. And I will point towards that. First, from this big simulation, you have a big result is that here in red you have a simulation, in blue you have the observation. Each point is a galaxy. So you see that the large-scale structure is exactly what we expect with the simulation. So it's a big success for the CDM. You find exactly the same kind of filaments, and the power spectrum of galaxies are very good. So this is a success, but there are some problems. The problems are at the galaxy scale. For instance, you predict in the CDM that you have a large density of dark matter in galaxies. Why, in general, you don't see this dark matter, even in the Milky Way, you don't see it. You have also a lot of satellites that you don't see. So if I go just to illustrate that, for instance, what you predict by the model in the simulation is a peak of density as a function of radius here. Why? What you see is a core. So it's what we call cusp-core problem. Of course, we can by feedback, and we have to adjust the feedback either by AGN or by star formation to try to destroy the cusp, but it comes back, so it's still a problem. And also the number of satellites that you have around the Milky Way-like galaxies can be 1,000 or more, and you don't see all these satellites. So you have a problem of the nature of dark matter here. So that's why people have tried other candidates of dark matter. For instance, I come back with the standard model here, the standard model of elementary particles, where you have the quarks, you have the leptons, and so on. One thing to note is that these normal leptons, familiar leptons, they have a chirality which is left. That the chirality is the direction of the spin with respect to the direction of motion. And of course, why not to go to the symmetric one with a chirality which is right? So it can appear natural to say, well, we have not seen all the neutrinos, and there are 3 other neutrinos, maybe with another chirality. And these neutrinos are completely sterile, that is, they are not interacting with a weak force, because we will see the neutrinos, the electric neutrinos, and all these neutrinos, we see it, even if it is difficult, but we have telescope to see the neutrinos. But these will not be seen, of course, because they are dark matter. But they can have any mass that you can imagine. So, and they are warm dark matter, in between hot and cold. But you have some constraints, in fact. You have the constraint because we don't see the matter in the filaments. In fact, the dark matter must be in the cosmic web, in the filaments. How can we see the filaments? They are not emitting, but we can see by absorption. Absorption in front of quasar, you see a spectrum of quasar, and after the redshift of the quasar, you have a forest of lines of Lyman alpha, which is the main line of hydrogen, and it absorbed in this line. And you can see that you have different prediction of the structure of all this cosmic web with this line that we have not with emission but with absorption. And then we have constraint on the mass, which cannot be too small, because then you will destroy the small-scale structure that we see in this filament. So this is a constraint. And another constraint, which is even more, is that this sterile neutrino must disintegrate also. And I have not time to go into the detail, but if you look at the parameter, the mass of neutrino and the interaction, all the colored part of this diagram are ruled out. And what is possible is the white. So you see that we have a small range of parameters still possible. So it's not very probable. And also Catherine, which is an experiment to detect directly the mass of the neutrino, they say that they don't detect this neutrino. So we have to wait for another particles. Well, now we have a lot of range of masses for these exotic particles. And I will speak about this, the last one, that is making some new simulation, which is the axion, not really the action, but the axion-like particles. The axion was there to solve the problem of symmetry CP. I don't enter into details from nuclear physics, but here we are extending that to a very, very small particles. You see 10 to the minus 22 eV, while here it was tera electron volt. So 34 orders of magnitude, a huge range of particles. And this very small particle, why is it so small? It is so small because we want to explain the core of dark matter, which is in each galaxy. So the core would be in this framework. It will be a soliton made of the Bose-Einstein condensate of these are bosons, and they are condensing in the center. And of course, they must have the Bragg length, a quantum length, in fact, if you want, that is very large, and it should be 3,000 light years, which is very large for quantum particles, a little far-fetched, but anyway. And then people have made some simulation with these dark matter particles, which is a quantum particle. You have to solve this Schrödinger equation and the Poisson equation, gravity and quantum mechanics. And of course, since it is a quantum particle, you have fluctuations. You know that there are fluctuations, even in the void, you have fluctuation. Here's quantum fluctuation don't damp because they are quantum of origin. Here you have two galaxies in interaction. You have this core, which is the Bose-Einstein condensate in the center, and you have a lot of fluctuation, which constrain the galaxy, because if you have this in the dark matter, it will hit the baryons, and you have thick disk, in fact. So it gives you constraints. And for instance, when you make a simulation with the cosmic web, where the galaxies are forming in the filaments, you have quantum fluctuation also in the filaments, and you have several quantum fluctuation at any scale: the core, the galaxy, and the big large-scale structure. So you see how it can be constrained even if we don't see the particle. Now I will finish my presentation with the last possibility, modified gravity. And if you take the Confucius proverb here, catching a black cat in the dark of night is the hardest thing over, especially if there is no cat. If there is no dark matter, of course, it's very difficult. So here the idea was come back from Milgram in 1983, so more than 40 years. It's still there, so it means that it is survivor with all the difficulties. And the idea is that you have to change the gravity in the weak field regime. Here you have the acceleration, which is the force of gravity per unit mass. So when you are above this, which is a very weak acceleration because it's 10 orders of magnitude lower than the gravity that you have on Earth, so 10 orders of magnitude, then you have the ratio of the dynamical mass that you measure by gravitational length or rotation of galaxies or whatever, and the visible mass. So this ratio is 1. That is, you don't need dark matter. All the visible mass is equal to the dynamical mass. When you are below this acceleration, that you see that this ratio increases, that the need of dark matter is increasing at weak acceleration. So you have to change the gravity at weak acceleration. That's why there's only astronomers that can make experiment there, because in all the solar system, you are in a strong acceleration. And you cannot test the Einstein theory is very valid for all the solar system, even for the Oort cloud. So the main things with hand waving is that the acceleration when you are going to very small acceleration is not in 1 over r square, but 1 over r. That's why we have a flat rotation curve without adding dark matter. Okay. So it's a degeneration. Either you'd say the Einstein law or Newton law is still valid and I have to add a lot of dark matter, or I change the law and I have no dark matter. So it's like the Neptune and Vulcan. So there is a lot of success of this for galaxies, even for dwarf galaxies which are dominated by dark matter, even for the center of the galaxy. You can explain the rotation curve and even the wiggles here, which are due to baryons, and when there is dark matter, you cannot explain these wiggles. Here we can have also going down, so it's not completely flat, in fact. Sometimes it's flat, sometimes it's not. And you can explain the Tully-Fisher law by construction, because this is from the flat rotation curve. So for galaxies, it works very well. We have made some simulation also to say if this is stable, because people with the CDM said, well, we need a dark matter halo to stabilize the disk of galaxies, but not, because here you have stronger gravity, so you stabilize also, and you can make all the bars, the spiral, and so on. So galaxies, it works very well. But you have also other domains where it did not work very well until recently. For instance, when I explained you that all these that you see in the Planck satellite, the oscillations, acoustic oscillation, that, of course, you had a restoring force due to the dark matter. And all this, the third peak, for instance, was due to the restoring force of dark matter. So if you have no dark matter, how can you explain that? But then you have a recent addition to this Mond theory by Skordis and Zloznik, where you have a scalar field that can explain only with baryons. You can explain this restoring force here, and also can explain the power spectrum of the fluctuation and the galaxies. So all the early universe can be, and we are waiting for the simulation, and I think David Mota is making some simulation there, so I'm anxious to know what is the result. And also there is a problem known in the bullet cluster, and this is well popularized, so I explain why. Here you have in red the X-ray gas, hot gas, that are on the two clusters that are colliding on the plane of the sky. You have a bullet here that was coming from here and is colliding. And then, of course, the gas is stopping in the middle. But you see the blue is a dark matter, well, dark matter plus visible matter, total matter. And the galaxies the galaxies are point-like. So when two clusters collide, they don't see each other, they cross, and they don't collide, of course. The gas, yes, stop in the middle, but the galaxies pass, and also the dark matter. You see in blue, the dark matter also has passed. So people said, well, you have separated dark matter and baryons, but it is not the problem that it is separated, because in a galaxy, for instance, like a Milky Way, you have all the baryons in the center, and the halo is out apart, so it's already separated. The problem is that in all clusters, you have a problem. The acceleration is not weak enough that you have the boost of the modified gravity. So you have to add something in clusters to try to explain cluster even in the Mond. But you have some resource here, is that you don't know where are all the baryons. In fact, when you look at the visible galaxies, even in you add clusters where you have hot gas, you see only 6% of all the baryons, which is very small because the baryons is only 5% of the total. So it's 0.5% of the total that you see, in fact. Of course, you can see, as I've described, the Lyman alpha absorption, and you can maybe, of course, Lyman alpha normally is an atom, it's neutral, but you can extrapolate to the ionized version, and you have 18% of the Lyman alpha. You can have also the WIM, warm, hot Why one hot? Because if it is too hot, you will see it in X-ray. If it is too cold, you will see it in the alpha. So in the middle, you don't see it. So it can be some dark baryons there. But anyway, even if you compute all that, you have 2/3 of the baryons that are not identified. You don't know where they are. So you can put some of these baryons in clusters and you solve the Mond problem. So it's a possibility. But you know that we are too much freedom to constrain, in fact, the model. That's a problem. When you have less freedom, you will be able to solve the puzzle. So I finish here. Now I try to explain you that we have degeneracy here. First, you have in galaxies the X-ray hot gas that is a lot more baryons that discovered Zwicky. So we have discovered a lot of things, but we still have not about half of the baryons. We have exotic dark matter. We don't know what it is, and we have candidates that are not as probable as before, or we have modified gravity. And then I leave you. You have plenty of work to do with all the students and postdocs here. Please help us.
Thank you very much, Françoise. This was very exciting, and it's clear we have a lot of work to do.
Yes.
I open the floor for one question.
One question.
Okay.
It's normal that you have no ideas because for decades we have no ideas. You can give him the microphone? Or? Okay.
Hi. Yeah, so I was a student in 1999 or something like that, and dark matter was a hot topic back then as well. Where do you think the solution to this eventually will come from? How do we know that we're not here talking about the same things in 20 or 30 years from now?
Yes, you're right. We don't know if we will discover something. I'm more optimistic about the dark energy, finally, even if it is discovered more recently, because there is a satellite like Euclid that will try to have the baryon oscillations like that are frozen in the baryons, like the oscillation that I've shown you. And yes, you will measure the expansion of the universe at different epochs, and you have at least, you will know the nature of dark matter, dark energy. But the dark matter will be taken a lot more time, I will say, because the particles are still not visible. We have also, I have not time to talk, but you have indirect detection by the annihilation, because I told you that they are not annihilating at all in the universe, but in the dense objects, for instance, in the sun or in galaxies, they are still dense enough that they can collide and annihilate. So you could have gamma rays. From that, people have looked at gamma rays, and there is nothing. So they are really difficult to detect. And maybe after a while, modified gravity will win the course. So I don't know. But modified gravity, at least you can predict in the future the progress. For dark matter, I don't know. For the direct detection of dark matter, it's less optimistic.
Yeah, I'm sorry that we don't have time now for more questions because the program is rather tight.
Yeah.
But we are lucky that you continue the evening with us, so we still have time to take questions offline.
Okay.
I'd like to thank you for giving this lecture.
Thank you. Yeah, thank you very much. Thank you.
And this will be easier for you to take home.
Thank you.
Thank you very much.
Thank you.